A massive star explodes in space, piercing the cosmos with an enormous beam of energy. Astronomers call it a gamma-ray burst.
We say that a gamma-ray burst shines with the light of 1 billion trillion suns.
Intense radiation hits the Earth's atmosphere. It destroys ozone and creates a sun-blocking smog in what becomes a global disaster.
I recognized that, aha, these two things in combination really represented a 1-2 punch for life on this planet.
A gamma-ray burst may have caused one of the worst mass extinctions in prehistoric history.
One of the first things people ask is, what does this mean for us?
With 300,000 gamma-ray bursts happening every year, what would happen if another one hit the Earth?
Society would really, in a lot of ways, be blasted back to the Dark Ages.
In a universe filled with the spectacular and bizarre, life on planet Earth may be exposed to a deadly threat. It is called a gamma-ray burst, and even if one happens at a vast distance from the solar system, it could destroy us.
It would irradiate Earth as if 100,000 atom bombs had gone off just outside our atmosphere.
Earth would not experience a shock wave or heat from the distant explosion. Instead, a beam of invisible gamma rays would act like a science fiction death ray, ripping into the stratosphere.
You would see a very bright flash in a particular spot in the sky, like a new star, and then the whole sky would go white.
The flash comes not from the explosion itself, but from the gases in the atmosphere, which glow when attacked by the high-energy gamma rays, and start what would become an environmental disaster.
It would destroy about half of the ozone layer on the Earth. And that means that more ultraviolet radiation would be coming down and hitting the surface of the Earth, and that would have the major effect of life on Earth.
This sounds like science fiction, but it may have happened before. A new theory proposes that a gamma-ray burst caused one of the worst mass extinctions in our planet's history. It happened 450 million years ago, at a time we now call the Ordovician period.
The Ordovician mass extinction is the second most severe extinction that has ever afflicted life on this planet. Far more severe than the extinction that eliminated the dinosaurs.
At the end of the Ordovician period, the land was practically bare, but the oceans were teeming with life. Then, for reasons that have yet to be fully explained, more than half of all species vanished from the face of the Earth. Recently, some scientists began considering a gamma-ray burst as a possible cause. One of them is astrophysicist Brian Thomas.
In this case, we've got the beaming coming
In
right
2005, Thomas was studying gamma-ray bursts while working on his PhD at the University of Kansas. GRBs, as they are known, are the most powerful explosions in the universe. A gamma-ray burst results from the sudden collapse of a supermassive star at the end of its life. It sends out narrow jets of gamma rays, so powerful they can be detected across the entire universe.
A gamma-ray burst, you're not going to see it coming. It's something that we would have little or no hope of actually defending against.
Thomas and his colleagues calculated what would happen if a GRB exploded deep in interstellar space, more than 6,000 light-years away. A light-year is the distance it takes light to travel in 1 year at the rate of 186,000 miles per second. It means the gamma-ray beam takes 6,000 years to reach the Earth. But even so far away, the burst could create a grim scenario for our planet. Gamma rays were first identified in 1900, when traces of them were discovered coming from uranium. But few people paid attention to them until atomic bombs destroyed Hiroshima and Nagasaki.
Many died, and the number of deaths kept mounting from day to day.
Radiation was known to be harmful, but the deadly effects on bomb victims came as a surprise to many. The damage to human tissue caused by radiation is measured in units called REMs. A safe dose is only 5 per year. But victims within a mile of the Hiroshima bomb received 400 REMs, much of it from gamma rays. It was enough to kill 60% of them within 30 days. The estimated figure for initial deaths at Hiroshima is 66,000. Radiation deaths would raise that to more than 200,000. Gamma rays are dangerous because of their intensely high energy. They are at the extreme high end of the electromagnetic spectrum, above the most powerful X-rays, and far beyond the domain of visible light and other waves in the spectrum. Still, gamma rays from space don't penetrate to the Earth's surface.
The Earth's atmosphere is thick and shields us. And that amount of material is enough to stop any gamma rays coming from outside the Earth's atmosphere.
If a gamma ray burst were to hit the Earth, the atmosphere would take the hit for us. Environmental scientists estimate that in just 85 minutes, it would have suffered damage so grave it would take a decade to recover. The high-energy beam would blast apart molecules of the two principal gases, oxygen and nitrogen. Single atoms of each element would then be free to recombine. In the chemical chaos, nitrogen and oxygen join to form a soup of dangerous nitrogen oxide compounds.
The nitrogen oxides, both the NO and the NO2, destroy ozone catalytically, and this is something that we've known for a long time.
Atmospheric scientists also know it only takes a single molecule of nitrogen oxide to destroy up to 1,000 molecules of ozone. The gamma ray burst modeled by the University of Kansas would destroy 40% of the ozone, our only protection against the sun's deadly ultraviolet light. UV at the surface would soar by 80%.
If you're showering the surface with lots of ultraviolet radiation, you're obviously going to kill a lot of things off right away.
Then there is nitrogen dioxide, a foul-smelling gas produced in the wake of the gamma ray beam. Spreading worldwide, it would cover the planet in an ominous brown haze.
That brown haze would block out sunlight and would initiate a period of global cooling that could last for months and would also have quite a dire effect on life on Earth.
With such serious consequences for the planet, the University of Kansas scientists wondered what clues might be found in the fossil record to show evidence of a burst in prehistoric times.
It's not unlikely that one of these may have occurred throughout the history of life on Earth, and as we study what has happened to life throughout its history here, this is one of the pieces of the puzzle that may explain some of the mysteries that we see in the record.
Mysteries like the great mass extinctions in Earth's distant past. Thomas sought the answer from paleontologist Bruce Lieberman.
I'd never heard of a gamma ray burst before my colleagues in the astronomy department talked about them.
Lieberman found a possible connection between gamma ray bursts and an event that occurred 450 million years ago during the late Ordovician period. Fish were just beginning to evolve, but the oceans teemed with primitive marine animals, such as mollusks and trilobites.
Trilobites are now extinct, but back in the Ordovician and in earlier times, in fact, they were the dominant form of life on the planet. They're arthropods. Their closest living relatives would be the horseshoe crabs.
For 45 million years, 2,000 different species of trilobites flourished in the Ordovician. But then, something suddenly went wrong.
And at the very end of the Ordovician, trilobites take a huge hit. About 65 to 70% of all species in the marine realm at that time go extinct.
Many scientists blame the Ordovician mass extinction on a global cooling, an ice age. there was a sudden drop in temperature which could have killed off many trilobites, but not as many as actually disappeared.
Basically, we needed some more oomph to explain how this many species could have been lost.
Brian Thomas and the Kansas Astronomy Department had a theory. They explained how a gamma ray burst might not only have frozen the Earth, but also depleted the ozone, creating a dangerous surge of ultraviolet light.
And these two things in combination really represented a 1-2 punch for life on this planet. I recognized that, aha, this is exactly the type of pattern that we see at the end of the Ordovician.
The harsh ultraviolet was lethal to plankton, the microscopic creatures living near the ocean's surface. They had no shielding. Lieberman concluded that any trilobites whose larvae swam near the surface would have lost all their young, becoming extinct in short order. That's why 70% of them suddenly vanished. An earthly chill coupled with an ultraviolet spike. It was a serious double whammy.
Usually when you look at anything biological, 1 and 1 is 3. You can handle what's coming at you from this side, or you could handle what's coming at you from that side, but you can't handle them both. And so usually when there's more than one stress, if it's cold and ozone or whatever it is, it's usually much harder than handling one at a time.
If the University of Kansas scenario is right, and a gamma ray burst did strike the Earth 450 million years ago, could it happen again?
The event that would happen at 6,000 light years might happen a few times every billion years.
The whole of human history is just an instant compared to such massive timescales. That means the chances of a GRB endangering mankind on the Earth are remote. And yet, the scientists tell us not to dismiss them.
We can't say there was one 450 million years ago and there will be another one 450 million years from now. It could happen essentially at any time.
What would happen if a gamma ray burst were to occur? How would Earth fare against the most explosive force in the universe? A force that until a few years ago was a complete mystery. Until the 1960s, gamma ray bursts were completely unknown. They were discovered accidentally during the Cold War at the height of the nuclear arms race. When the Nuclear Test Ban Treaty was signed in 1963, the U.S. launched Project Vela, a fleet of satellites to detect any Soviet tests that might violate the pact.
They detected flashes of gamma rays on these satellites because they had gamma ray detectors. Nuclear bombs make flashes of gamma rays.
In 1967, one of the Vela satellites picked up gamma rays no nuclear bomb could have made. They appeared as a large double peak on a graph of data about 8 seconds long. The first burst astounded scientists because it came not from Earth, but from outer space.
There's nothing we love more than a surprise, and this was really surprising.
But gamma rays are not visible to the naked eye, so the readouts from scientific instruments were the only sign of the spectacular display.
When a gamma ray burst is happening, it outshines everything else in the entire universe in gamma rays. And so that was really a completely new phenomenon and not something that anybody would have expected.
It was also alarming because until then, the only thing we knew to cause big gamma ray flashes were nuclear explosions. The Vela satellites were not equipped to pinpoint the positions of GRBs in the sky or how far away they were.
Because these gamma ray flashes were so unexpected and there was no real idea of what could produce such a flash of gamma rays, the whole astronomical community and the public too were quite puzzled by what was causing these flashes of gamma rays.
By the 1970s, astronomers had detected a few dozen gamma ray bursts and came up with still more theories on what caused them. They even considered alien warfare in deep space.
liftoff of the Space Shuttle Atlantis and the Gamma Ray Observatory, seeking out the explosive forces of the universe.
Gamma ray bursts remained a perplexing mystery for nearly 30 years. In 1991, NASA launched the Compton Gamma Ray Observatory, the first instrument dedicated to finding out just where gamma ray bursts came from.
So the next step was, are they coming from sources in the Milky Way, or are they coming from outside the Milky Way?
For 9 years, Compton detected an average of 1 burst a day. Its instruments were able to plot their rough positions on the stellar map. Scientists expected to see them along the narrow band in the sky representing our galaxy, the Milky Way.
Because Vela had discovered these bursts as being so bright, we thought that they were coming from somewhere nearby our solar system in our own galaxy, and that they would be distributed on the sky like the Milky Way is.
What they discovered is that the gamma ray bursts were evenly distributed over the whole sky.
Because gamma ray bursts happened all over the sky and not just in the Milky Way, it was strong evidence that they could come from galaxies anywhere in the universe. Here's what it meant. We know the size of our own galaxy, so any GRB within the Milky Way would be no more than 70,000 light-years away. But if they can occur in any galaxy, they could be up to 12 billion light-years away. If GRBs are really that far, the brightness of their flashes would mean they had to be more powerful than anyone ever imagined.
The reason we all get excited is because they're just big, big explosions, and we love working on such energetic things.
We say that a gamma ray burst shines with the light of 1 billion trillion suns. It's just an enormous amount of energy.
So of course one of the first things people asked, just human nature, is what does this mean for us? And it was immediately realized that because these bursts were such powerful explosions, that if one went off in our own neighborhood, let's say just in our own galaxy, for example, it could have a serious effect on our Earth and on its atmosphere.
But to prove that GRBs came from great distances, astronomers needed more precise measurements than the Compton satellite could give them.
It was clear that in order to understand them, we have to pinpoint exactly where are they on the sky.
Enter the Dutch-Italian satellite called Beppo-Sachs. In 1997, it was the first to zero in on a precise position for a GRB. Its accuracy was comparable to eyeballing a basketball at the distance of half a mile. It allowed optical telescopes, both on the ground and in space, to find the explosion's afterglow.
Gamma ray burst doesn't just disappear. It glows even after the burst is gone. It leaves some signature in even invisible light.
Seeing the visible afterglow was tremendously important. Unlike gamma rays, visible light gives us the ability to see a spectrum and its red shift, the yardstick astronomers use to measure distance in the universe. Every star or galaxy has a signature spectrum. If a galaxy is near, it may look like this. But if it is farther away, the spectrum is shifted toward red light. The greater the red shift, the farther away the galaxy. Beppo-Sachs transmitted its coordinates for a GRB for the first time on May 8, 1997.
I just happened to be at the Palomar Observatory then with my group, and I got a telephone call telling me about the burst. We dropped everything else and decided to go and look after it.
At vast distances, the optical images of gamma ray bursts were no more than tiny specks in the starfield. But even these could be analyzed for their red shift. For the first time, a GRB's distance from Earth was revealed.
This one was a so-called redshift of 0.8 or so, which translates into a distance of several billion light years from the Earth. At that point, the puzzle of gamma ray burst distances was solved.
It was a critical breakthrough, and as more GRBs were measured, it was clear most were amazingly far away.
The typical distances for those bursts measured by Beppo-Sachs were 8 billion light years away. They were halfway across the visible universe.
It was very exciting in the sense that it was sort of the greatest result you could hope for as an observer in terms of being the greatest distance that anybody expected to find the gamma ray bursts at, and therefore the largest energies, the highest luminosities. These really were the most violent phenomena in the universe.
Imagine taking the sun and annihilating it with an anti-sun and turning it all into gamma rays in 10 seconds. Well, it's hard to imagine, and it was hard for the theorists to imagine too. In fact, we couldn't.
What kind of celestial dynamo could create a burst so powerful that for a few seconds it explodes with the energy equal to all the other stars in the universe combined? In a universe fraught with danger, the most powerful menace may be the gamma ray burst. Strange enigmas, their existence is as puzzling as their nature.
We've discovered a lot of very exciting things, but there's still a whole lot more to learn about these. Gamma ray bursts are still very mysterious.
Since the breakthrough discovery of 1997 showing the tremendous distance of GRBs from the Earth, a constellation of satellites and ground observatories has continued to scan the skies for more gamma ray bursts. A massive case file has accumulated evidence to reveal the true nature of these strange phenomena. Consider GRB 990123. The name is in code, GRB for gamma ray burst, 99 for the year of its detection, 1999, 0123 for the month and day, January 23rd. The Hubble Space Telescope photographed the visible evidence, a bright spot within the glow of its host galaxy. Data from the burst provided a clue that jumped out at astronomers.
So there was a suspicion from the very beginning that gamma rays coming out of explosions are coming out in beams or jets and not in all directions at the same time.
Evidence for the jets appeared in the light curve, a chart showing the brightness of the burst as time passed. First, the optical afterglow faded gradually, but then it dropped off abruptly in what's known as a jet break. It was the unmistakable signature of an intense energy beam as it slows down. And if bursts shoot their gamma rays out in jets, it means we only see GRBs aimed right at us. There are far more that we never see.
For every one we see, there's about 300 that shot off in another direction. The guns were pointed somewhere else besides our head and we didn't see them. So there's about 300,000 gamma ray bursts per year in the universe. And that's about 1 every 100 seconds.
Cosmic jets are well known to astronomers. This photo from the Hubble Space Telescope shows one streaming from galaxy M87, 60 billion light years from Earth. Jets are generated by objects like rapidly spinning black holes, which some theories put at the heart of gamma ray bursts.
I believe, and a lot of us believe, that a gamma ray burst is the birth cry of a black hole. That it says here, a black hole has been born. And there's very little in astronomy more fascinating than a black hole.
A black hole is a region of matter with infinite density. It creates gravity so intense that not even light can escape it. But black holes were not the whole story. The next pieces of the puzzle fell into place when GRBs were connected to another well-known phenomenon, the supernova.
In 2003, March 29th, 2003, a spectacular event occurred.
The gamma ray burst of that day came from a galaxy close enough to be measured in detail. In the course of a month, the spectrum of the afterglow went from a largely flat line to one with complex bumps and wiggles. It was almost identical to the spectrum known to belong to a supernova.
And that was the first very clear-cut evidence for a supernova gamma ray burst association. Since that time, there's been about 4 others. And we now think that it's quite common, maybe not universal, maybe it is universal.
A supernova is a massive explosion that happens when a large star, at least 8 times more massive than the Sun, burns out all its nuclear fuel and crashes inward on itself, forming an ultra-dense neutron star. In the process, it blows off its outer envelope in a spectacular display. Now, astronomers had 2 key clues. First, GRBs sent their gamma rays out in jets. Second, they were usually accompanied by supernovae. The 2 facts together seem to confirm a theory for the cause of gamma ray bursts.
And since 1993, there had been a theory that gamma ray bursts were produced when the centers of massive stars collapsed to black holes, the so-called collapsar theory.
Collapsar is the astronomical nickname for a supermassive collapsing star. The big star's death is the wildest ride in the universe, and it begins with something much bigger than a supernova. A collapsing star large enough to be called a hypernova.
This is a massive star, about 20 times more massive than the Sun, in some sense much younger than the Sun, only about 10 million years, but nevertheless it's dying.
Deep inside the collapsar, the core is shrinking as it spins at incredible speeds. The center becomes so dense that it forms a black hole. Explosive forces can't escape the spinning disk, so they shoot out in jets at the poles, the path of least resistance. The jets plow through the stellar layers. The turbulence of subatomic particles colliding at nearly the speed of light generates the powerful gamma rays that make these explosions unique. Within seconds after the black hole forms, the jets break the surface of the star as the gamma rays begin rocketing toward the farthest reaches of the universe. It ends with a hypernova. Internal shock waves boomerang within the stellar body, flinging its gaseous envelope into space, leaving the optical afterglow as a hallmark of the cosmic violence.
These gamma ray bursts, as has been said many times in the press, are the biggest, brightest bombs since the Big Bang itself.
The GRB lasts anywhere from 2 to 100 seconds. Its power may be understood by showing how it would affect the Earth. 6,000 light-years away, it could cause a mass extinction, as a GRB may have done in the ancient past.
It's like having 3,000 megatons of bombs go off in the Earth atmosphere simultaneously.
But what if it happened closer? Instead of 6,000 light-years, just 1,000.
The megatonnage would be about like 100,000 megatons of nuclear bombs. It's like standing a couple of miles from a Hiroshima bomb everywhere on the surface of the Earth. There might be an event within 100 light-years. Then things get very, very bad. It blows away the atmosphere, creates tidal waves, it starts to melt the surface of the Earth. Now, if you want to get even more extreme, you could say, what about the nearest star? There is a 1 chance in a million in the life of the Earth that something might happen as close as Alpha Centauri. And then you would truly incinerate the Earth. It would be left, the rocky part and everything would be left. But it would be billions and billions of megatons, as they say.
Fortunately, astronomers have found most hypernova GRBs in very distant young galaxies that are quite unlike our own. It's thought that only these young star systems can produce such GRBs, and we may be safe from them. But there is another kind of gamma ray burst in the cosmos.
Gamma ray bursts come in basically 2 flavors. There are the long duration gamma ray burst and the short duration gamma ray burst. The dividing line is about 2 seconds.
Long gamma ray bursts last anywhere from 2 to 100 seconds or more. But the short bursts last less than 2 seconds, some of them as short as the blink of an eye. These short bursts are far more mysterious than their longer cousins. They seem to have little to do with supermassive stars and hypernovae. Instead, They come from very different processes. Processes that may well take place in our own galaxy, where the Earth cannot possibly avoid them. A remarkable spacecraft is now spearheading the effort to solve the mystery behind short gamma-ray bursts. Launched in 2004, it's called SWIFT, for the bird of the same name, known for its ability to switch directions quickly in flight.
We have ignition, and we have liftoff of NASA's SWIFT spacecraft on a mission to study and understand gamma-ray bursts throughout the universe.
Looks pretty bright.
For nearly a decade, astronomers on the ground were able to see only long gamma-ray bursts, those lasting from 2 to 100 seconds or more. Short gamma-ray bursts remained a puzzle because they were over before satellites could calculate their positions. SWIFT changed everything. The SWIFT satellite is a technological acrobat designed to repoint itself in seconds whenever a gamma-ray burst is detected.
Locating a gamma-ray burst on the sky is like pinpointing a flashbulb that goes off in a stadium. It's such a fleeting flash of light that you can't tell where it came from.
SWIFT takes direction finding to the next level of precision for gamma-ray bursts.
I'd say we've definitely seen it.
This is definitely a burst. I mean, you can see how bright it gets.
Mission control for the SWIFT satellite is at Penn State University. When SWIFT locates a burst, the team immediately issues an alert.
There's a widely distributed message that goes out to observatories all over the world, telling them that this burst has gone off, what kind of burst it is, and that they should point their ground-based telescopes at the burst.
500 astronomers across the globe received the SWIFT alert. Among them are Ido Berger and Alicia Soderberg, working at the historic 200-inch Hale telescope on Palomar Mountain, north of San Diego.
Hello? Hey, Ido. Yeah, the new burst, I think you may want to trigger observations on it.
The astronomers are chasing the GRB's optical afterglow.
Let's just start with a quick exposure, let's say 20
Quick
seconds.
image, yeah, 20 seconds. The gamma ray burst itself only lasts for a few seconds to a few hundred seconds. The visible light component that accompanies the gamma ray burst actually lasts for several hours, days, and sometimes even weeks.
We built the SWIFT satellite specifically to be able to determine the location of short gamma ray bursts. In the summer of 2005, we finally got a short gamma ray burst and made the discovery that we'd been waiting for, which was the position on the sky and what was causing the short gamma ray bursts.
When it came to the long and short, many scientists had believed that gamma ray bursts had two distinctly different origins.
The long gamma ray bursts are produced by the death of a massive star. The short gamma ray bursts are thought to be produced by the merger of neutron stars.
Neutron stars are dead remnants of stars. They have about 6-mile radius, and they orbit each other, and as they orbit, their orbit slowly loses energy, and they collide in a massive explosion that we always knew would make some kind of flash of light, and was predicted would make a gamma ray flash.
When SWIFT finally got the first location for a short gamma ray burst in 2005, astronomers aimed their telescopes and discovered that the GRB came from an elliptical galaxy, a kind of star system with an indistinct round or oval form.
This is a galaxy that has only old populations of stars, not young massive stars that you'd expect making collapsars and hypernovae. These elliptical galaxies are exactly where you'd expect to find old, burned-out stars like neutron stars.
The case isn't proven, but the clues point strongly to neutron stars as the cause of short gamma ray bursts. The problem for Earth, the Milky Way may have many such stars.
We do know of cases in the Milky Way where there are neutron stars that someday will come together. And so, unlike the other kind of gamma ray burst, we can predict with some certainty that something like that will happen in the lifetime of the Milky Way.
the occurrence of gamma ray bursts, either long or short, is about 1 per million years in a galaxy like ours. One that occurs very close enough to do biological damage might be this rate of a few 100 million years.
The last gamma ray burst may have struck Earth 450 million years ago. There is no way of predicting when the next one could come or how close it would be. This very uncertainty and its potential danger drives even skeptics to ponder disastrous events like these and how humanity might survive.
When they do occur, even if they're rare, they're extreme events and have high magnitude impacts. And thus we're interested in these high magnitude rare impacts. We're interested in preserving our own species.
According to the scenarios outlined by University of Kansas scientists and other astronomers, the disaster would begin deep in space, little more than a few thousand light years away. Massive collapsars may be very rare in the Milky Way, so a colliding pair of neutron stars will be the most likely culprits. The crash lasts less than 1/100th of a second, and the result is two powerful jets of gamma rays, shot like cosmic cannonballs from each pole. One of them is aimed directly at Earth.
If a gamma ray burst went off anywhere in our own galaxy, it would be a spectacular display on the sky.
A brilliant flash fills the sky as the gamma rays tear into the atmosphere. Earth is suddenly stripped of its protective ozone, and the surface is bombarded with deadly ultraviolet radiation. Temperatures drop as a brown haze blocks sunlight, and life on our planet hangs in the balance. Earth is a sitting duck when it comes to gamma ray bursts. They may happen near enough to harm us only once every 300 to 500 million years. We wouldn't see it coming. But if one ever hits us, our future would take a hairpin turn.
The first thing that people would notice, suddenly they would be walking around, and then in the middle of the day or the night, there would suddenly be this new sun in the sky. And that would be the first indication that something wrong is going to happen.
Gamma rays themselves are invisible, but the atmosphere absorbs them and re-emits them in visible wavelengths.
Well, you'd likely see some sort of bright flash. Fairly brief. These events are pretty quick. You also would probably end up blind.
And a lot of the gamma rays would excite oxygen atoms, the same sort of process that makes aurora, so you'd have a very bright green sort of sky and a luminosity like that of the sun.
As in the Ordovician period 450 million years ago, the atmosphere's gases would react quickly. 40% of the ozone would disappear, and a tea-colored layer of nitrogen dioxide would begin to envelop the planet.
This will change the color of the sky so it becomes a brown haze. And this would happen over a period of hours. It would happen really rapidly. That has consequences. Looking up at the sky, the entire, even in the daytime, everything would have a brown hue to it.
A global electromagnetic pulse, like one from a nuclear bomb, would suddenly attack any unshielded electronics. At the Operations Center for NASA's Earth Observation System, technicians would notice the first signs of something wrong. Data from satellites would abruptly stop. Delicate circuits in the world's most sophisticated devices would be fried.
It's going to wipe out satellites. It's going to create power surges worldwide. It'll blow out the power distribution. Depending on how close you get, but I think even the typical gamma ray burst would probably fry a lot of the electronics, a lot of the computers. Everything would be in total disarray.
Society would really, in a lot of ways, be blasted back to the Dark Ages.
Few people would realize a true mega-disaster had begun. A handful of undamaged instruments at the National Weather Service would detect the 80% jump in deadly ultraviolet light. Forecasters would try to issue frantic alerts, but with mass communications crippled, no one would be able to hear the warnings. In the nighttime sky, sheet-like auroras were once welcomed as beautiful spectacles created by the solar wind. But now, the altered chemistry of the atmosphere would replace the normal auroras with a ghostly green glow persisting for weeks. Then the first winter would come, perhaps the worst winter in history. If the gamma ray burst has been close enough, it might generate a layer of brown nitrogen dioxide, blocking as much as 10% of the sunlight, a disastrous amount.
At 10% reduction in sunshine, we start to see snow staying in big areas of the land masses through the summers, because 10% is sort of what was needed to make ice ages.
Snow and ice would appear in places where it is never expected. A society with its technological infrastructure already crippled would struggle to survive. Sunny Los Angeles could be blanketed in snow, and Pasadena's Rose Bowl may as well be renamed the Ice Bowl.
You'd presume that you could get to snow in Los Angeles. It has happened in harsh winters within historical time, and this would be a much bigger kick to the climate system than the usual fluctuations that brought the snow to Los Angeles.
The oceans, less vulnerable to the cold, would take their worst hit from ultraviolet light.
If you are a life form that lives in a particularly exposed environment, surface of the ocean, say, and you don't have a lot of protection, then you're very likely to be outright dead.
Destruction of the ozone layer would expose phytoplankton to deadly levels of UV.
Phytoplankton live in the ocean. They're simple algae that photosynthesize and therefore depend on sunlight. If you lose a large percentage of phytoplankton from the marine food chain, you're going to get a collapse of the ocean ecosystems.
In coming months, water at the coasts may turn red and orange. Nitrogen compounds in the atmosphere would produce nitric acid rain, harmful to life at first. In time, though, it can act as fertilizer, creating ominous red tides of poisonous algae, among the few species that would have survived the initial ultraviolet onslaught. Dead fish would wash up on beaches in the first sign of a worldwide famine of epic proportions. On land, crops may fail, weakened by the 1-2 punch of ultraviolet light and suddenly colder climate.
We're vulnerable to climate change because we do depend on a very few species for our food crops. A late freeze could kill an entire crop.
There would suddenly be far fewer places in the world where food can be grown. Humanity could face hunger on an unprecedented scale.
And so if you start looking at a failure of the food system, the growing system over much of the planet, we don't have huge reserves. We don't have years and years of food that are just sitting away. I don't even know how we could do that.
After a gamma ray burst, much less human population could be supported on this planet. Probably on the order of 5 to 10% of the population that we see today could be supported, at least for several decades after a gamma ray burst.
Across the United States, cities and towns would be deserted, and the infrastructure would wither. Electric plants with no one to run them would mean the lights would go dark. Fuel refineries with no workers would leave our gas tanks empty.
After a gamma ray burst, life on this planet, particularly for humans, would be really grim. All of the benefits of civilization that we depend on today are going to be gone.
It would take a decade for the atmosphere to return to normal, but by then the damage would be done. With the country able to support only 10% of its former population, 270 million Americans would have succumbed to disease and famine.
So if I hadn't stored up a lot of canned goods and army rations and other things that are non-perishable, I really wouldn't want to be around, to be honest, and I just hope that I didn't last very long.
Some astronomers estimate there are 100,000 binary neutron stars in the Milky Way. Nobody knows if or when any of them could collide to create a gamma ray burst that would hit the Earth. But with evidence pointing to a burst in our ancient past, it's clear we can never be completely safe.